Hello everyone, and thank you for joining today's session on ArcGIS GeoEvent Server, leveraging real-time GIS. My name is Gregory Christakos, and joining me is my colleague RJ Sunderman. We're both product engineers for GeoEvent Server, which will be the topic of our discussion today. We're also joined by Greg Tiemann as our moderator for the Q&A session, which will be following today's presentation. As far as today's agenda goes, we'll be covering the following topics that you see before you. If you are here today for an introduction to GeoEvent Server, this presentation will have a little something for you. If you have a little experience already, though, with GeoEvent, and you want to see what's new at 10.8.1, we are excited to be showing you some of the new enhancements we've made to the user experience. And then, of course, if you're hoping to catch a brief demo of what GeoEvent Server can do and get a deeper dive into how it's configured to do that, we've got something for you as well. We do have a lot to cover in just 45 minutes, so let's dive in. Before we can talk about GeoEvent Server and its real-time capabilities, we first need to understand what is real-time data. And in its simplest form, real-time data is observational data. Traditionally, this is thought of as things that move, whether it be cars, ships, planes, or maybe even storms, just to name a few examples. But increasingly, with the advent of connected devices and the Internet of Things, real-time data can also take the form of data collected from stationary sensors. So some examples of this might be a water meter or a gas gauge, or maybe data from a weather station. But then, of course, real-time data can also come from things that just happen, such as lightning strikes, accidents, traffic alerts, or tweets. All of this is streaming data that we can leverage within GeoEvent Server to perform real-time analytics and notification. To take a step back here, when we look at real-time data and ask, how does this fit within the broader ArcGIS Enterprise system? The answer is found in the 5 key capabilities that GeoEvent Server provides. We'll be spending some time reviewing each of these capabilities in more depth, but the first is ingestion. GeoEvent Server enables the ability to bring in all the different types of real-time data that we just discussed. The second key capability is analytics. So GeoEvent Server can be used to perform real-time analytics and filtering of data. This is, of course, to detect patterns and trends in most situations. This is a little bit different from traditional GIS, where batches of historical data may be processed and analyzed well after the fact to detect past patterns or trends. The third key capability is storage. GeoEvent Server also enables the ability to store high volume and high velocity real-time data, whether it be in a system file, an enterprise geodatabase, the spatiotemporal big data store, and so forth. The fourth key capability is visualization. Simply processing and storing your real-time data doesn't quite tell the whole story. Most oftentimes, we want to be able to visualize this data. GeoEvent Server enables this through the use of different services, such as map services, feature services, and stream services. The last key capability is actuation. Once GeoEvent Server has brought in real-time data, processed it, and then detected patterns or incidents that are unique to us, it can then use this information to adjust the behavior of things in its environment. This is important when it comes to IoT devices, as GeoEvent may be used to facilitate processing messages for those devices to respond to.
Let's delve a little deeper into the key capabilities Greg just introduced. Data ingest is how data from sensors is brought into GeoEvent Server. Out of the box, configurable inputs enable you to connect to virtually any sensor network: commercial, industrial, scientific, municipal, public, or private. If an external web server or web service provides its data through an accessible REST services API, GeoEvent Server can either query to get the data or receive data being pushed to it. If data at rest is not available, you can configure TCP, UDP, or WebSocket connectors to receive or subscribe to receive the data. GeoEvent Server can adapt data from self-describing formats such as JSON, GeoJSON, and XML and ingest the data for processing. It can also be configured to adapt simple delimited text, such as sensor data broadcast as comma delimited values, or read data logged to a system data file. The point is, data from virtually any data source can be transmitted and adapted for ingest into GeoEvent Server. Once data has been brought into GeoEvent Server, it is natural that you will want to apply some processing to the data. GeoEvent Server includes over 24 different types of processors, enabling you to design and publish custom data processing workflows. Some processors are used to calculate derivative values or perform pattern matching and string manipulation. Others help you perform extract, transform, and load operations, mapping data from one schema to another. There are processors enabling you to enrich sensor data with information from external sources using attribute or spatial join operations. And a few of the processors act as monitors, watching for conditions of interest and updating the duration from when a condition is observed until it is no longer relevant. Illustrated here is one of our geometric processors, used to create a polygon buffer about an event record's point, line, or polygon geometry. You can also use our GeoEvent Server Java SDK to develop your own custom processors, or for that matter, custom inbound or outbound data connectors. The GeoEvent Server product gallery has pre-compiled samples of processors other teams at Esri have developed, such as a motion calculator, a reverse geocoder, and a track idle detector. Often, the source code for these sample processors and connectors have been open sourced and made available on GitHub. If your team has a Java developer, the implementation samples can be tailored for your specific need or used as a springboard to develop a completely custom processor. GeoEvent Server can also be used to apply real-time filtering to sensor data, discarding data whose attributes do not satisfy a specified threshold or those which do not satisfy a spatial condition. Illustrated here, we see a sample concept of a filter discarding event records which are not either blue or orange. Spatial relationships are evaluated against a set of geofences you register with your GeoEvent server. You can perform a one-time load of geofences using the geometry from feature records you maintain in a geodatabase and expose through a feature service. You can also actively synchronize geofences by configuring GeoEvent Server to periodically poll a feature service for updates, or subscribe to a stream service for feature record broadcasts. Frequently, we think of geofences as areas of interest and want to determine when an asset's point location is inside or outside. Spatial relationships are not limited to point and polygon tests, however. For example, you can register the fixed point locations of critical assets as geofences and use GeoEvent Server to evaluate spatial relationships, such as whether an event record's geometry crosses, contains, intersects, or is disjoint from a specified set of geofences. This enables interesting use cases, such as receiving and processing a projected area of effect for changing weather conditions. You can use GeoEvent Server to perform real-time analysis and determine when required hazardous weather protocols need to be enacted. A third key capability offered by GeoEvent Server is control over how you want to disseminate processed event data. GeoEvent Server does not inherently store data it receives and processes. It is your choice whether you want to persist event data, for example, as feature records in an enterprise geodatabase. Many times users do want to leverage a feature service to either add or update feature records. Data received in real time often arrives at high velocity or as large blocks of data from a sensor network. When your concept of operations exceeds what you can do with a traditional relational database, there are options to use a NoSQL spatial temporal big data store. Greg will be looking at this in just a moment when we talk about data visualization. If you do not want to store data as feature records, you can broadcast data from processed event records using a stream service. Stream services leverage WebSocket technology to broadcast streams of data formatted as feature records. Any solution component downstream from your GeoEvent server can subscribe to the stream service's WebSocket to receive data as it is processed in real time. We don't have time this morning to delve into all of the different options for data output. GeoEvent Server can push data to an external web server's web service or WebSocket, write data out to a system file, broadcast the data via a TCP or UDP WebSocket, or write to an Apache Kafka topic. There are also options for notification, but now I'm stealing some of Greg's thunder, so I'll yield and let him talk about those capabilities.
Thanks, RJ. The fourth key capability of GeoEvent Server is the visualization of processed real-time data. Like storage, visualizing real-time data is entirely optional when working with GeoEvent Server. In fact, there may be times where the data you bring into GeoEvent does not have a spatial component to it whatsoever. But where there is a spatial component, GeoEvent Server can be used to facilitate sending this data to a variety of different services. All of these different service types can then be consumed in client-side web applications, such as a web map or an operations dashboard, to then display the features. In the example you see here, a simple feature service has been used to display the real-time location and attribute data of buoys as feature records in a web map. This process data, of course, is stored in an enterprise geodatabase. In certain scenarios, though, it can become quite difficult to distinguish discrete features when they start to accumulate in the thousands or millions on the web map. And so one of the key benefits behind using map and feature services with the spatiotemporal big data store is the unique aggregation capabilities that come along with it. By specifying a feature threshold, we can control when discrete features begin to automatically aggregate and render as bins. These bins can either indicate a simple observational count, or they can be configured to display some sort of statistic such as average temperature recorded in an area. It's important to note that as we zoom back into an area of interest, big data feature services support rendering discrete features that fall below that threshold we've specified. Stream layers are another way of visualizing real-time data from GeoEvent Server. Using WebSockets, streaming data can be broadcasted from GeoEvent Server directly to the client consuming the stream layer. It's actually the web client that can then be used to uniquely display streaming data. For example, in the web map shown before you, the stream layer is used to display unique feature renderings for each aircraft. Each aircraft is essentially symbolized with a different color. The aircraft are also shown heading in a certain direction. This is made possible in the client by specifying a heading value for each feature. This is obtained as a part of the streaming dataset. And we'll see more of this in the demo later, but stream layers can also be used to render breadcrumbs for displaying historical tracks. The fifth and final key capability of ArcGIS GeoEvent Server is actuation. So GeoEvent Server offers several methods for actuation. Two popular ones are sending an email or a text message. And we can see in the example before us that as soon as this monitored vehicle leaves the geofenced area, an email is generated notifying a supervisor of the event. GeoEvent Server supports HTML code for formatting notifications as rich text, email, or SMS text messages. With this, it's possible to invoke values from the source event data for the message. This is how, for example, we see driver 1 is headed southwest at 55 miles per hour instead of a more generic message which might be crafted as the driver is outside the zone. We often think of notifications as something such as an email or text message sent to a person, but GeoEvent Server can also be used to facilitate change on network-connected devices. In the example that we see here, different types of processed event data can be used to trigger a response on the corresponding device in the cloud. GeoEvent, for example, may facilitate these types of messages as part of an HTTP POST REST request. But now that we've had a more in-depth look at the key capabilities of GeoEvent Server, I'm going to hand things back to RJ, where we'll take a closer look at how these concepts are realized through GeoEvent services.
Thanks, Greg. Let's switch now and take a look at some improvements made to the design and publication of GeoEvent services. Before we get started with discussing the critical components of a GeoEvent service, let's describe the essential pieces of a GeoEvent service. In its simplest form, a GeoEvent service is what allows you to define the flow of real-time data, or GeoEvents, from an input to an output. At a minimum, a GeoEvent service must have at least one input and one output connector. Adding processors and filters to a GeoEvent service is optional. Processors are generally used to perform some operation on an event record, calculate a value, create a buffer, enrich the event record, etc. Filters are generally used to test attribute and/or spatial conditions and discard event records which do not satisfy the specified criteria. Often, when configuring inputs, outputs, processors, and filters, you need support from other critical elements, such as GeoEvent definitions, geofences you've registered with the GeoEvent server, or server connections you've registered to an ArcGIS server or ArcGIS Enterprise portal. Let's take a look at how each of these critical elements are accessed as part of the design and publishing of a GeoEvent service at 10.8.1. You start by launching the GeoEvent Manager web application. From the home page, you click Add Service to begin designing a new GeoEvent service. This takes you to the Service Designer. From here, you can add the required input and output to your GeoEvent service. Notice that I do not have any pre-existing inputs or outputs created. At 10.8.1, I create them from here, in the Service Designer, to help keep my focus on what I'm doing, designing and publishing a GeoEvent service. Clicking Input beneath the New Elements grouping, I can drag to add a new input to my GeoEvent service. I'm presented with a panel which allows me to review different types of inbound connectors. I can list the available inputs either by how the data is being conveyed to GeoEvent Server, for example looking at transports, or switch to look at available inputs by how the data I expect to receive might be formatted, for example looking at adapters. Clicking Output, I can drag to add a new output to my GeoEvent service. Again, I am presented with a panel which allows me to review different types of outbound connectors, either by transport or adapter. For the purposes of this demo, let's suppose I've configured a new input and a couple of new outputs. Returning to the New Elements grouping, I can click and drag to add a new processor to my GeoEvent service. A pull-down lists the different types of processors available out of the box. In the interest of time, suppose that I've configured a couple of new processors and a couple of new filters. Hovering near the edge of any node allows me to click and drag a connecting line to define how event records should flow.
To successfully create a GeoEvent service, we often need to make adjustments to various site settings. And so at 10.8.1, we're excited to announce that it's now possible to access and edit many of these settings from here in the Service Designer. For example, I can click on GeoEvent definitions where I can see all of my existing definitions before me. I can make any sort of necessary edits to them or delete them should I choose to do so. I can also access geofences. Here I can see not only all of my existing geofences, but I can import new ones or manage my synchronization rules. We've also exposed data stores as another setting here. If I click on this, I can see all of my registered server connections and folders for further use. At this point, our GeoEvent service is ready to be started. Now by default, any inputs or outputs you configure begin their life in a stop state as we see here. But you can just as easily start them by right-clicking and choosing Start Output. Now as I do this, you'll notice that in the lower right-hand corner, there's a newly designed status indicator that briefly displays to let me know that an action was successful. In this corner, we'll also find any warnings or errors should there be any. The takeaway from this is that all of this is new in the Service Designer. You no longer have to cancel an action and navigate to another web page just to review or configure a component of your GeoEvent service. You're now able to do what you need from within the Service Designer, keeping your focus on what you set out to do, to design and publish a GeoEvent service.
Each connecting line between two nodes can be considered a pipe through which event records are flowing. At the bottom of the screen, I can click to expand a new utility, a GeoEvent Sampler. Clicking to enable the sampler, I can select any of the connecting lines and see the event records flowing through the pipe. In the sampler window at the bottom of the screen, you now have a scrollable list of the latest event records routed from the input to the first processor in the GeoEvent service. Clicking a different connecting line enables you to see the event records flowing from the processor to the first of the two filters. When the connecting line between the second filter and processor is selected, we see that we have a problem. The sampler displays an indicator that a process is running, but no data is being displayed. Clicking on the route into the filter, we see event records are being routed to the filter, but the speed of each event record seems to hold a null value. When I double-click to check the configuration of the first processor, I see that a field has been left unmapped. Correcting the processor's configuration, I can click Publish to commit the changes to the GeoEvent service. Then refresh the GeoEvent Sampler's display, check to see that the speed values are no longer null, and now when I select the route coming out of the filter, I see event records displayed by the sampler.
You can also use the GeoEvent Sampler to compare event records. If I click to select a route whose event records are flowing into a processor, and then right-click to select a route coming out of the processor, you'll notice that the GeoEvent Sampler now displays two side-by-side frames. This view allows me to compare event data before entering the processor to the same event data that's been presumably modified and is now coming out of the processor. This is useful for making sure that data schema, attribute values, or even event record geometry is changing as expected. In the upper right corner of the sampler, you can click the settings gear icon to change how data is represented. Currently, we are sampling event records in JSON format, but we can just as easily change this to text. And as soon as we click refresh to sample more records, our data is displayed in a more compact delimited text format. We can just as easily adjust how many event records we choose to sample in total. By default, the sample size is set to 10 events, but we can easily adjust this to 1 or 100. And it's important to note that any change I make to my GeoEvent Sampler settings will be persisted. So if I go ahead and click on this new route coming out of the filter, I can see that the sampled events are still showing up as delimited text. But for now, I'm going to change my data type back to JSON and increase my sampling size from 10 to 100. A big reason why I might keep my data type as JSON when sampling events is so that way I can actually visualize the geometry of my sampled event records before me. This is done using a new feature of the GeoEvent Sampler called the Event Viewer. If I go ahead and sample more events here to bring in more data as JSON, you'll see that on the right there's a new icon for the Event Viewer. Clicking on this will open up a small, lightweight web mapping application that allows me to visualize my current sample of event records. This is really cool. For the first time, while we're still designing and publishing changes to our GeoEvent service, we're able to see a preview of the event records as features on a map. Now, just to take things one step further, let's close the event viewer before us. And I'd now like to comparison sample data before and after the range-fan calculator. Here I could see I have more sampled events coming in as JSON, and if I click on the event viewer, I'm actually returned two different web map displays. On the left, I have my original points before the processor, and on the right, as I zoom in here, we can see that there are the newly constructed range fans after the processor. I can just as well zoom around or even click on individual features to see the attributes. There's also a locking feature, so I can pan around both maps at once if I would like to do so. What's useful about this new event viewer functionality is that we're able to quickly and easily confirm that our event record geometry is changing in the ways that we expect it to. We don't need to implement some other temporary feature service or stream service just to visualize and confirm the same thing. And with the GeoEvent Sampler overall, as well as all of the other changes you've seen today, you can be confident that your real-time data is being processed in the way that you designed it to be. Having just seen how real-time data is handled by GeoEvent Server through the concept of GeoEvent Services, we'll now explore a demo where we'll see the output of what a GeoEvent service offers us in real time. In this demo, we'll be tracking drones and monitoring for alerts based on conditions that are important to us. And more broadly speaking, this is to provide us situational awareness through the use of GeoEvent Server. Now, before we get started with the demo, let's assume for a second that we're part of an engineering firm of some sort, and that our daily work involves operating in the field with the use of drones for imagery purposes. Now, a lot of us might be aware of this already, but there's certain rules and regulations that govern the use of commercial drones. For example, there might be certain no-fly zones where our drones cannot go. This could be something such as an airport's airspace, a high-security area, or so forth. And so in red, we have a geofenced area representing our airport and its airspace. And for the purposes of our demo, we're treating this as a strict no-fly zone for our drones. Additionally, drones tend to be a pretty hot topic when it comes to residential areas, and so maybe as a standard operating procedure, we don't want to fly our drones within 400 feet of these buildings. And so in blue, we have a different type of geofence which indicates our residential areas we want to avoid. Just as equally of importance, we're treating this as a strict no-fly zone. Now, I can go on about different aspects of operating commercial drones, but the last thing I want to point out here is that generally speaking, drones aren't supposed to go above 400 feet in altitude, so this is another condition we'll want to keep an eye out for. Having set the stage for some of the things we want to maintain a situational awareness of, we'll go ahead and start this demo. Now here we see we have the two of our drones' positions being reported in real time through the use of stream services. We have a breadcrumb trail showing the previous locations as well. And on the right here, you see that our drone just entered that airport's no-fly zone airspace. And so we can go ahead and pick that up as an alert here and display it accordingly. Not only do we have the drone's ID and the reported time that this happened, but we also have the name of the geofence that it went within. We could potentially use this information to let the operator know on the ground not to return to that area. On the left here, we see a different type of notification occur. This red target indicates that there is an altitude warning. In other words, our drone exceeded that 400 feet in altitude that it was not supposed to. And so we can go ahead and visualize this alert or send a notification to the operator. Now at this point, we see that the drones are returning to their starting position. And while the drone on the left might not be actively capturing the imagery anymore, we see that clearly it flew over those residential areas. And so we can go ahead and visualize those alerts.
Here's the GeoEvent service that enabled the demonstration Greg just shared with us. Let's take a closer look at the event routing, filtering, and processing the GeoEvent service is performing. First, we see an input connector receiving data from the GeoEvent simulator. Drone position reports are being received over a TCP socket connection in real time. A field mapper processor is used to adjust the schema, mapping data from one GeoEvent definition to another. The position reports being received have a field named Drone ID. We want to rename this attribute field to be UAV ID. A field mapper can also be used to perform basic data type conversions, such as numeric to string or long integer to a date time. Event data emitted from the processor is routed to a stream service connector. The output formats the event records data as Esri feature JSON, and then broadcasts the data via a WebSocket. This is what enables us to display the location of the drone in real time using a web map. Stream layers have the ability to display a breadcrumb trail of previously reported drone positions. Looking at another portion of the GeoEvent service, we see data passing through a filter and a geotagger processor. The filter is configured to evaluate a spatial condition to see if the drone's location is inside any no-fly zone. Remember that in order to perform a spatial relationship test, feature record geometries need to be imported and registered with GeoEvent Server as geofences. Only event records whose geometry is inside a registered no-fly zone are routed along to the geotagger. Drone positions which do not need to be displayed as warnings because they are not inside a no-fly zone are discarded by the filter. A geotagger processor is used to enrich each event record it receives with the name of the geofence it currently intersects. This is what enabled the web map to display the name of the no-fly zone as part of a web map configurable feature record pop-up. We also configured the web map to symbolize feature record geometry from the no-fly zone stream using a warning icon.
One aspect of the GeoEvent service that wasn't shown in the demo, but could just have been easily incorporated, is sending a text message notification when a drone is reported inside of a no-fly zone geofence. Using the same route that RJ had just discussed, we can configure GeoEvent Server to send the same geotagged event records to the text message output. The text message could even be drafted to reference the name of the drone, the time of the occurrence, as well as the name of the geofence it is inside. You may have noticed that along this route, we've also included an event volume controller processor. This was placed just before the text message output connector. We've added this to control the number of unique event records passed through as eventual text messages. Our goal here really was to ensure that only one text message is sent over a certain period of time, as seen here. Without the processor, we could potentially receive a text message each second that a drone is reported to be inside of a no-fly zone geofence, and this type of spam is certainly not useful. Using the event volume controller is just one strategy for controlling events sent from GeoEvent Server. There's certainly many others to consider though. In this final part of the GeoEvent service, we see that data is also passed through a filter and a field calculator processor. Unlike the previous filter we've seen, this filter has not been configured to evaluate a spatial condition. Rather, the filter has been configured to evaluate an attribute field to see if the drone's altitude has exceeded 400 feet. Only event records whose altitude is above 400 feet passes the filter. All other event records whose altitude is at 400 feet or below are discarded from processing. Event data that passes the filter is then sent to a field calculator, though. And in simple terms, the field calculator processor is used to compute some sort of value. For this demonstration, we've configured the field calculator to change the value of a string message field to exceeded altitude. This is what enabled the web map to display the message as part of the feature record pop-up once the data was passed to the stream service. To recap, here's the overall GeoEvent service that enabled the demo you just observed. We have one input connector in green where we receive the drone data over TCP. The data from our input connector is then sent to a series of different filters and processors to identify conditions important to us. These conditions were things such as when the drone entered a no-fly zone geofence or when the drone exceeded a certain altitude. After the data is processed and we've identified key events, we then pass this information along to different output connectors, and in this case, they're primarily stream services, for visualization and/or notification.
In our presentation today, we covered the key capabilities of GeoEvent Server. ArcGIS GeoEvent Server is the server role you add to your ArcGIS Enterprise to enable real-time data ingest, processing, feature record storage, and streaming broadcast. Data ingest is accomplished using configurable input connectors. Configurable filters and processors enable you to design and publish GeoEvent services, which are like small routines or programs applied to data you receive in real time. Choices in how you disseminate process data affect options for data visualization using web applications or operational dashboards. We reviewed how GeoEvent services are designed and published, highlighting some of the improvements to the user experience implemented as part of the 10.8.1 release. Key points to take away are the GeoEvent Sampler, enabling real-time preview of data during GeoEvent service design, and the access you now have to critical elements, such as GeoEvent definitions, geofences, and registered server connections. Finally, we took a brief look at a solution designed for receiving and processing position reports from an unmanned drone. The GeoEvent service designed for the demonstration included several different processors, filters, and output connectors enabling reported positions to be displayed on a web map, with symbolized alerts appearing when the drone's position was inside an unauthorized area. The solution also incorporated event volume control and an output able to format event data into requests an external server could handle to produce SMS text notifications.
Here are some additional resources. If you did like today's demo and you'd like to see it expanded upon, RJ and I did present an analytics-focused technical workshop earlier this year. Within it, we do expand on that drone demo and introduce several processors in more detail. So if you're interested, we do invite you to check that out at the following link. We also continue to add content to our online help documentation all the time. And in fact, we're working on a significant rebuild of our documentation, which should be out later this year. But here you'll find information about all the different components and content that we discussed today. So please give that a look if you're interested. Another great resource for GeoEvent Server can be found on GeoNet, where there's a plethora of technical blog articles as well as discussion threads. As a team, we are pretty active in this forum space, and so we're happy to help answer any questions that we can. And then lastly, a new instructor-led course for GeoEvent Server has been made available, along with other free resources from Esri Training. So if you're looking to get started with GeoEvent Server, we definitely invite you to give this a look as well. That concludes today's session. Thank you all again for joining us, and we hope you learned something valuable or new about GeoEvent Server today. I'm going to go ahead and hand things off to our moderator, Greg Tiemann, so that way we can commence the Q&A session.